Here's a dice problem which was asked in JPMorgan interview. The question says you play a game of rolling a six-sided die. For each roll, you can get the face value or re-roll it, and you can roll it up to three times at most. Suppose you are a rational person, how much would you pay to play this game? So the question is, you get a six-sided die, you have to roll it at most three times. After each roll, you have an option to either take the face value of the roll. So let's say you roll the die once and you get three. Now you can either take $3 and go away, or you can choose to roll again second time, and then a third time. So let's say you roll it for the second time, you get two. You roll it for the third time, you get five, say. So in the end, of course, you'll have to take whatever is the last roll. But at each turn, you have the option of taking the face value or the option of rolling it once again. So how much would you pay to play this game? That's the question. So essentially, what this tells us is we need to find what's the expected value of the amount that we are likely to win given this setup. Once we know how much we are likely to win, we can then decide how much would be the amount that we would be willing to pay to play the game. So let's see how we solve this. So in such questions, we use the backward induction approach. So we'll analyze it from the last roll and then move backwards, because at each step we have an option of either taking away the amount that we just rolled, or we continue for the next turn and take the expected value that we would likely get from the next turn. So you'll just see why we are starting from the third roll first. So this is, let's say, our third roll. On the last roll, we have to take whatever we roll. There's no re-rolls remaining, right? So the expected value, which we denote by E3 of the third roll, is simply the expected value of all the possible values given a dice roll, which is 1/6 of 1 plus 2 plus 3 till 6, which is equal to the average of 1 to 6 is 3.5. So this is the expected value that we are likely to get, we would get from the third roll. Now we move backwards and come to the second roll. So on the second roll, let's say you roll the die and you get a value of X. Now we have two options, whether we could keep X or we re-roll once, uh, and then we would move on to the third turn where we have the expected value of 3.5 as we just calculated. So what should we do? We should keep the roll if it's greater than 3.5. So we have the expected roll of the third turn, which is 3.5. If we get a value greater than 3.5 in the second roll, we take it. If not, we re-roll. So for values 4, 5, and 6, we take these values because these are greater than the expected value of the third turn. For values 1, 2, and 3, we should re-roll. So we re-roll on 1, 2, 3, and we keep 4, 5, and 6. Now, what's the expected value then of the second roll? So that what we are doing is we are taking the maximum of our roll. Let's say it's X and E3 for X between 1 to 6, which is all possible rolls. Sorry, this should be max. I meant to write max. Not. Let me just clear this up. So max of, okay, I'll use the same notation which used here, so to avoid any confusion. K and E3. So K is what we roll in our second turn, and E3 is the expected value from the third turn. So we are saying we take the max from these two. So K can take a value from 1, 2, 3 up till 6, and E3 is 3.5. So what this becomes is max of 1 and 3.5, or max of 2 and 3.5, till max of 6 and 3.5. Each with a probability of 1 by 6. So this becomes the first three terms would be 3.5 because 3.5 is greater than 1, 2, and 3. And then 4, 5, and 6, the last three terms would be 4, 5, and 6. So this is what this will expand into. So E3, as we calculated, is 3.5. So if you roll less than 3.5, it's better to re-roll and hope for a better outcome. If you roll 4, 5, and 6, you should keep the value. So this was our expression. And we expand this. The first three terms would be 3.5, and the last three terms would be 4, 5, and 6. So this gives us this expression E2 equals 1 by 6 times 3 times 3.5 plus 4, 5, and 6. This is equal to 4.25. So the expected value of our second roll is 4.25. Now we continue with the same approach and we come on to the first roll. So the first roll, you can either accept the value or re-roll using E2 as your baseline, the expected value. So the exact same approach that we do, we have to take the max of either K, comma E2, where E2 is 4.25. So this 4.25 here, and K is, this would be summation from K is equal to 1 till 6. So this is 1 and 4.25, 2 and 4.25, 3 and 4.25, and so on up till 6 and 4.25. So the first four terms, the maximum would be 4.25. So when we expand this, we would get 4.25 in the first four terms because 4.25 is greater, and the last two terms, 5 and 6, is greater. So it becomes 5 and 6, and each of them is with probably 1 by 6 of a dice roll. So E1 becomes 1 6 times 17 plus 11, which is 4.66. So what would be the final answer? How much? The question was how much would we be willing to pay? The maximum rational price to pay for the game is the expected value obtained from the optimal strategy, which is approximately 4.67. We have rounded 4.66 to two decimal places. So this is the amount that